Welcome back to the video for solving problems in elementary spectroscopy. This continues from what I just did for 4 problems in the video tutorial 2, and we shall start with the next problem, namely problem 5, in which we are asked to do the following: determine the fraction of molecules in the V is equal to 1, 2 and 3 state relative to the ground state V is equal to 0 for the molecule bromine monofluoride. I think there are some typographical things here. The frequency of the transition is 669.7 centimeter inverse. Okay. So, what the problem says, at T is equal to 1000 Kelvin, and when nu is given by 669.7 centimeter inverse for the molecule bromine monofluoride, okay, you are asked to calculate the number of molecules in the V is equal to 1 relative to the number of molecules in the V is equal to 0 state. Okay. This is a very elementary problem in the sense it looks at the Boltzmann population at equilibrium, and since vibrational states for this single degree of freedom are non-degenerate, the ratio is given by the simple exponential factor, namely exponential minus E V is equal to 1 by kBT divided by exponential minus E V is equal to 0 by kBT. And you know the difference between V is equal to 1 and V is equal to 0, the energy, the answer is h nu, okay, and nu is given as 669, therefore is h c nu bar. Therefore, the delta E to the minus delta E by kBT for this ratio n equal to V is equal to 1 to n at V is equal to 0, this delta E is given by h c nu bar, okay, and the nu bar is given as 669.7 centimeter inverse. Therefore, what you have to do is to ensure that you use the right units, namely it is given as 669.7 into 10 to the 2 meter inverse times 6.626 into 10 raised to minus 34. This is h, this is nu bar, times 3 into 10 to the 8 meters per second, and this is joules and the meter inverse. And so, what you see is the delta E is given as joule second, okay, joule second times that, therefore, the answer is given in terms of joules. So, this can be calculated, and kBT is 1.38 times 10 to the minus 23 joules per Kelvin, and it is calculated at 1000 Kelvin. So, that is given as joules. Okay. Therefore, delta E by kBT is a numerical exercise, okay, for you to do that and take the exponential of minus that in order to calculate the ratios of n between the two different levels. And the only thing that you have to do for 2 and 3 is that for 2 the energy difference between E0 and E2 is 2h nu, and for 3 it is 3h nu. Therefore, you will see that the relative populations in the first, second and third exciter state drastically come down to very, very small values. That is the purpose of this exercise, to show that in vibrational spectroscopy, the number of molecules in the higher energy levels is much less than the number of molecules in the ground state, and this number is less if the frequency is even more. Okay. That was the idea for this problem. Okay. Therefore, you can calculate that. Okay. The next problem is a formal process. it is basically asking you to write all the simple harmonic oscillator wave functions for n equal to 0 to n equal to 3. It is a textbook exercise, and most important for this is determine why the selection rule for vibrational spectrum of a harmonic oscillator contains only one line with the selection rule delta nu is equal to plus minus 1. That is important. Okay. Problem 7, and you are asked to write the harmonic oscillator functions. So, textbook exercise, please remember that the psi n is a normalization constant which is a function of n, and then it is e to the minus alpha x square by 2 times h n of root alpha x. Okay. Therefore, what is alpha? Alpha is equal to square root of k mu by h bar square. So, the k is the force constant, mu is the reduced mass, and those are the only two parameters for this problem. Therefore, this is the vibrational wave function, and the h 0 is 1, h 1 of root alpha x is 2 root alpha x, h 2 of root alpha x is 4 alpha x square minus 2, and the third h 3 root alpha x is 8 alpha root alpha x cube minus 12 root alpha x. Please remember, this makes the whole expression dimensionless, because the alpha has a dimension of 1 by length, and therefore, you see that the harmonic oscillator x is the length parameter, it is a distance from the equilibrium for vibrations, and therefore, this whole quantity polynomials are dimensionless. So, these are the corresponding forms, and each one of them you have to multiply by e to the minus alpha x square by 2, and also put down the general formula for n. These are available in textbooks. But the second part of the problem is important, namely why the selection rule delta nu is equal to plus minus 1. Okay. Okay, this is a mathematical statement that the selection rule for transition between E n with the wave function psi n and E, let us write n double prime, n prime, psi n prime, n double prime. The selection rule for vibrational transition is due to the dipole moment matrix element which connects these two states. In fact, the transition probability, this is a statement, you have to take it from me. Transition probability for transition between n prime and n double prime, n prime and n double prime is given by the absolute square of the integral from minus infinity to plus infinity psi n double prime, psi n prime star mu, which let me not write, mu is the dipole moment here, dipole moment, okay, not the reduced mass, mu dipole moment psi n double prime dx. Therefore, mu is essentially mu naught times x, and this x keeps changing. Therefore, during vibration the dipole is created and changed, destroyed and so on, or increased and decreased. Therefore, this x is the operator, the position operator, and the mu naught is the constant for the permanent dipole moment, position operator. Okay. Therefore, the dipole keeps changing from mu naught to mu naught times x during the process of vibration, and the integral that you needed to calculate is psi n prime of x from minus infinity to plus infinity star mu naught times x, and then you have psi n double prime x dx. Okay. This is what is called the transition probability amplitude, and the absolute square of this is the transition probability per unit time, whatever units that you wanted to use. But the absolute square is the one which is connected with the actual process of transition between vibrational levels, and therefore it is important for this what is called the matrix element of the dipole moment operator. Between the two states x n prime and n prime, okay, n double prime and n prime. So, the calculation essentially boils down therefore to writing down, in the case of vibrational spectroscopy, the psi n's are given by the exponential minus alpha x square. So, let us write that from minus infinity to plus infinity. The normalization constant associated with psi n prime, which is e n prime, and the function is e to the minus alpha x square by 2 times h n prime root alpha x. This is psi, including this is psi n prime. Okay. And then you have x times the mu naught, and then you have e to the minus alpha x square by 2 h n double prime root alpha x dx. So, it turns out to be from minus infinity to plus infinity proportional to, let me drop the constants out, that is also an n double prime for the wave function associated with this state. Okay. That is a normalization constant for that state. So, this is the integral that needs to be calculated. It is called the transition moment integral. Transition moment integral. Now, without any further explanation, I will just make the statement that this integral will be non-zero only if, when you write that like that, the alpha x square by 2 add up, and then this integral will be non-zero only if n prime and n double prime differ by plus or minus 1, because it involves x. If it involves x square, then the dipole moment is now being considered as the square of the amplitude for vibration. That, I mean, those kind of things do happen when you talk about anharmonic states of the molecule and so on. The dipole moment in the lowest level of approximation is simply proportional to the length, and therefore what you see is the length x itself, and this is a harmonic oscillator model, and therefore the harmonic oscillator model, this integral is non-zero only if n double prime is n prime plus or minus 1, because of the nature of the Hermite polynomial. Please understand, the Hermite polynomials are odd and even, and so what you see here is that the integral becomes even only when n prime and n double prime and x, these three products give you an even function. But that argument should be very carefully stated, because this does not mean n and n prime can differ by 3. No, it does not work. This integral is still 0. It cannot differ by other than 1, and therefore it is a property of the wave functions, which results with the transition moments being connected only in the vibrational energy levels. If I have to write the potential energy and then simply write to the vibrational energies as something like that, n equal to 0, n equal to 1, n equal to 2, and so on, n equal to 3, the only transition that is possible that can be measured experimentally are these, because of the nature of the wave functions. Therefore, the transition moment integral needed to be introduced in order for you to understand this problem. Okay. this will not happen, okay, will not happen. So, vibrationally there is only one line for a harmonic oscillator corresponding to this frequency, okay. They are all the same, therefore, there is only one line nu bar, okay. That is the important point. Next problem, okay, I missed problem 6, so let us go back to problem 6. Okay. Problem 6 is on a Morse oscillator model. Okay. Please remember the Morse oscillator model, the energies are given as H omega E H bar omega E V plus a half minus, okay, here I am using omega E in terms of wave numbers, therefore, let me write this as H omega E and then minus H omega E x E V plus a half whole square. This is the Morse, this is the expression for the Morse oscillator energies. If we are writing this in terms of centimeter inverse, let us do one more thing. Let us get rid of this and let us write this as some nu E as omega E x E minus omega E times V plus a half minus omega E x E times V plus a half whole square. Therefore, all are in wave number units. Okay. Now, the problem that is given to you is BRF. Let me now read the problem. The problem given to you is that the vibrational frequency omega E and the unharmonicity constant omega E x E have been found from experiments to be about centimeter inverse, to be 669.7 and 3.869 centimeter inverse. And you are asked to calculate the first 4 Morse oscillator energy levels for this molecule and also the transition frequencies for the transitions V is equal to 0 to 2 and V is equal to 1 to 3. Okay. So, let us look at that. So, the nu corresponding to the vibrational quantum number V is omega E times V plus a half minus omega E x E, this is the unharmonicity V plus a half whole square. So, when V is equal to 0, nu 0 is half omega E minus 1 by 4 omega E x E. Nu 1 is 3 by 2 omega E minus, this is 3 by 2 squares, therefore 9 by 4 omega E x E. And likewise you are asked to do that for 4 levels, isn't it? So, nu 2 is 5 by 2 omega E minus 25 by 4 omega E x E. And the last one, omega 3, is 7 by 2 omega E minus 49 by 4 omega E x E, because the second term is a square, V plus a half square. So, everything is a square here. So, these are the expressions for the 4 energy levels of the Morse oscillator. Okay. Now, you are given omega E and omega E x E. So, this is given as 669. So, if you write nu 0, it is 669.7 by 2 centimeter inverse, and the other is 1 by 4 minus 1 by 4 times 3.869 centimeter inverse. So, you know that, and therefore, in a similar way you can calculate nu 1, nu 2, nu 3. Now, what is important is the next step, which is V is equal to 0 to V is equal to 2. So, what is delta nu E? 0 to 2. If you look at that, it is 5 by 2 omega E minus 1 by 2 omega E, that is the first term. 5 by 2 omega E, first term, minus 1 by 2, this is between 2 and 0. And the next one is minus 25 by 4 omega E x E minus 25 by 4 omega E x E minus 1 by 4 omega E x E. And so, what you have is 2 omega E minus 6 omega E x E. So, this is the second frequency, and likewise delta nu E from 1 to 3 is 7 by 2 omega E minus 1 to 3 is 1 is 3 by 2 omega E minus 7 by 2 corresponds to 49 by 4 omega E x E minus omega 1 corresponds to 1 by 9 by 4, 3 by 2 whole square, therefore 9 by 4 omega E x E. So, what you have is 2, this is also 2 omega E x E minus 40 by 4. So, it is 10 omega E x E. What do we gain from this process of calculating? And that is important. It is not just this problem. What is important from this problem is that if you look at it, the Morse oscillator model, which has a potential energy or VFR, if you remember, has something of this kind that we saw in another problem. If you look at it, the lowest energy level is half omega E minus 1 by 4 omega E x E. The next energy level, if you look at it, is 3 by 2 omega E minus 9 by 4 omega E x E. The difference between the two is 2 omega E x E, the enharmonicity term is 2 omega E x E. But if you go to the next level, the levels are closing in. That is the purpose of doing this exercise. The levels are closing in. That is, successive energy differences are smaller, because you remember this omega E x E term is negative to any omega E term, because you see any nearby energy level, say V is equal to 0, V is equal to 1. If you look at the transition between two nearby levels, you see this is 0 to 1 is omega E minus 2 omega E x E. But from 1 to 2, if you look at that, V is equal to 2, it is again omega E, but 1 corresponds to 9 by 4 and 2 corresponds to 25 by 4, that is 5 by 2 whole square. Therefore, the difference between the two is 4 omega E x E. So, the second energy level difference V is equal to 1 to 2 is smaller than the first energy level difference. Therefore, the Morse oscillator energy levels actually coalesce, they converge, and so what you see is that there are many lines that you can see in the vibration spectrum, because not every one of them is not equal to every other thing, they are different. And also in Morse oscillator it is possible for you to have multiple transitions, V is equal to 0 to 2, V is equal to 1 to 3 and so on. Therefore, you see Morse oscillator gives you a real model of what is called the vibrational spectrum, a spectrum, not one line. That is the purpose for doing this exercise. Let us go to problem 8 now. Problem 8 talks about molecule boron trifluoride and it asks you to calculate the 3 principal moments of inertia and identify the time. And it also asks us to calculate all the energy levels of this molecule for the rotational quantum number j up to and including 3. Okay, first of all, this is a symmetric top BF3. So it's actually an equilateral triangle that you can draw B, the 3 fluorines, and these are the bond distances between the 3 fluorines. They are identical. Okay. This is what you have. Now you are asked to calculate all the 3 moments of inertia. It's a very simple exercise. So what are these axes? So we can choose one axis. Let me use a different color. Let me choose one axis as the axis that passes through one of the bonds. Okay. The center of mass is right where the boron is because of the symmetry of the system, and therefore the second axis, which is perpendicular to that, is that axis again passing through the boron, and the third axis is perpendicular to the plane of this screen. Okay. That's a third axis. So you have what is called the IX, IY and IZ axis. Okay. Now it's easy to see that with respect to these 2 axes, this axis as well as this axis, the moments of inertia that you calculate are identical. Let us do that. Okay. The BF bond distance is given. Please remember these angles are 120 degrees. Therefore, you can see that if we calculate it for this axis, we call it as the, we'll call it as the X, Y, and the Z will be up. Yeah, that's fine. So let's call this as X axis. One fluorine is on the axis, and therefore it doesn't contribute to the moment of inertia. Mu I, mu 1 or 1 square, call it as 1, that's 0 or is 0. The other 2 fluorine atoms, if you think about that, this is 60 degrees, this is 60 degrees, and this is the fluorine boron bond distance. So if you write this as RBF, this distance as RBF, then this perpendicular distance of the fluorine atom from the bond axis is RBF times sin 60. Okay. So you get the Ri, the R1, R2, this is 2, this is 3. So M2 R2 square plus M3 R3 square. If you want to calculate this for the moment of inertia I along the x axis, because M1 R1 square is 0, the mass of the fluorine atom being M of F, we have R2, which is the perpendicular distance, is given as the RBF sin 60 degree whole square and into 2, because this atom is also exactly at the same distance from the axis. Therefore, this is what you have, sin 60 is root 3 by 2. Therefore, you have MF 3 by 4, 3 by 2. So, it is 3 by 2 MF or BF square. Okay. That is the first one. Now, what about this axis? Let us look at this axis. If you look at this axis, all the 3 atoms are away from this axis. The distance of, let me now remove some of these things and make it easier. The distance is this, the distance of this atom is this, they are both identical, and it is easy to see that this distance is, and also this one, So, let me redraw the boron trifluoride. This is the bond, this is the bond, and so the axis that we have is this. So, we wanted to calculate this distance and we wanted to calculate this distance, they are both the same, okay. And then you have this is simply RBF whole square, it contributes F1, this is F1, this is F2, this is F3, this is boron. Okay. Therefore, this you can see immediately as this is again 30 degrees. So, this distance will turn out to be or BF2 times sine 30 whole square times 2 of them, because F2 and F3. So, that would be the answer. So, this gives us as RBF square MF1 plus all the RBFs are the same, therefore, this is sine 30 is 1 by 2. So, it is 1 by 4 times 2, it gives you RBF square times 1 by 2 MF. So, this is the total moment of inertia I, and this is also 3 by 2 or BF square MF. So, this is identical to the moment of inertia about this axis, that is also 3 by 2. Now, what about the perpendicular axis? If you talk about the perpendicular axis, it is something which is like that. Therefore, you see all the 3 atoms are away from this axis by exactly their bond distances. Therefore, the perpendicular distance from this axis is actually the BF bond distance. So, you have 3 times MF times the RBF square. So, this is what you get, this is for IZ. Now, it is interesting that IX plus IY is equal to IZ, okay, because you have 3 by 2 here, you have 3 by 2 for the previous case, and this is 3. This is a planarity. In fact, this is a planarity condition for the moments of inertia. That was the reason for including this as an example. Therefore, you have to sit down and try to calculate the moments of inertia from simple geometries, and you must know the actual structure, the equilibrium structure of the molecule, the bond distances and bond angles, and then go back and calculate the rotational constants using that and see in experiments whether that is the rotational constants you get and so on. That is the reason for this particular problem. Okay. Next. The next problem talks about rotational spacing between successive lines of HCl as 20.8 centimeter inverse, and it is asking you to calculate the bond distance. It is also asking you to determine the number of molecules in the level J is equal to 4 relative to J is equal to 3, and then one more thing, namely determine the level in which there is maximum population, that is T is equal to 300 K may be assumed. Okay, it is important to remember that in the case of rotations, the line intensities actually increase as you go from J is equal to 0, 1, 2, 3, etc. And if you talk about the intensity here, the rotational line intensities increases something like that, and there is a maximum. And this we remember is due to the fact that Nj divided by Nj, let us write it as prime for the upper level, double prime for the lower level. This is given as the new J prime, the degeneracy of J prime and the degeneracy of new J double prime. Therefore, the ratio times exponential minus delta E from J prime to J double prime divided by KBT. So, the difference between vibrational population and the rotational population in this case is that there is a degeneracy factor associated with nu j prime and j double prime, and in the absence of any external field, the j prime level has a degeneracy, j prime level has a degeneracy of 2 j prime plus 1, and likewise the j double prime level has a degeneracy of 2 j double prime plus 1. Therefore, this problem asks you to calculate the energy level N j is equal to 4 divided by N j is equal to 3. This is second subdivision. The first division is the bond distance itself for RHCl. This is easy. Please remember the successive rotational lines when you write the intensities. The successive rotational lines are all differing by 2b. Okay, this is intensity, this is the wave number, they all differ by 2b, and therefore 2b is equal to 20.8 centimeter inverse. And you know B is given by the formula h by 8 pi squared IC, and therefore h by 8 pi square IC is 10.4 centimeter inverse. And since I is equal to mu R square, and in the case of HCl, mu of HCl is 1.008 into 35.456 divided by 36.464 times 1.6661 into 10 raised to minus 27 kilograms. Okay. Therefore, mu is known, R square is what you are asked to calculate. So, you write h by 8 pi squared mu R square C is equal to 10.4 into 10 raised to 2 meter inverse. Make sure that you use the same SI units because we are using kilogram and R is in meters. Therefore, you see immediately R is given as the square root of h by 8 pi squared mu C times 10.4 into 10 raised to 2. Okay. This is, and h of course is known, mu is known and C is known, therefore you can calculate R. Therefore, this is a very straightforward substitution formula. Okay. Now, the second is of course N j is equal to 4 divided by N j is equal to 3. Please remember E j is equal to 4, if you recall for the microwave spectrum of rigid diatomic molecules, it is HCB j into j plus 1. Okay. Therefore, for j is equal to 4, it is 20 HCB in terms of joules. Okay. That is why the H and C are here. For E, j is equal to 3, it will be 3 into 4, so it will be 12 HCB. Therefore, the delta E between j is equal to 4 to j is equal to 3 is 8 HCB, and you are given 2B as 20.8 centimeter inverse. Therefore, the delta E is given as 8 into HC into, this is 2B, therefore I would say 4 times 4 HC times 20.8 into 10 raised to 2 meter inverse. Okay. So, delta E is known and N j is equal to 4 to 3 is N j is equal to 4 divided by N j is equal to 3 is 9 to j plus 1 j is equal to 4 to j plus 1 7, and then you have e to the minus delta E j is equal to 4 to j is equal to 3 divided by kBt, where kB is 1.38 into 10 raised to minus 23 joule per Kelvin, and T is 300 Kelvin. Therefore, you can calculate this number by doing the numerical work. Okay. Now, the last section of this problem is to ask you what is the maximum, what is the value of J for which the intensity is maximum. The intensity is maximum, that is what is you are asked to do. And I think you must remember this formula that the the J max, this was discussed in the lectures, the J max is approximately the nearest integer to kBT by 2hCB minus 1/2. You have already been given 2B, you know T, you know HC. Therefore, whatever is the integer nearest to this number, this will not be an integer because the square root factor will not give you round integer value or half integer value for you to substitute. Therefore, take the nearest integer to this number as the J for which the population is, for which the intensity is maximum. Okay, that is that. So, we will come to the last problem. This is purely a classification of the molecules as spherical, symmetric or asymmetric tops, which is important for understanding the molecular spectroscopy, and therefore, we need to make sure that the geometry of the molecules are visualized and that you see that the moments of inertia about the three different axes, whether they are the same or whether two of them are the same and different from the third, or if all the three of them are different, you have to have a mental picture. And it is very clear from some of these, for example, the tetrahedron. Now, CBR4, it should be immediately obvious that this is a spherical top. The reason is tetrahedron is half the symmetry of the cube. So, you know that if you place this molecule in the cube, okay, and then you start worrying about what those moments of inertia are, you will immediately see that the moments of inertia are identical about any three axes, because this is one BR, this is another BR, and the third BR is going to be here and the fourth BR is going to be here and the carbon is right in the middle, C. Therefore, you can see that this is a tetrahedral molecule inside the cube. If you want to do that, it has half the symmetry of the cube. Therefore, you see that with respect to the structure, whether the axis is this or whether the axis is this or whether the axis is perpendicular to this face, the moments of inertia are the same because the molecules are ideally displaced from these axes by the same distance. Therefore, something should be immediately seen as based on the geometrical considerations that it is a spherical top in this case. Now, CHCl3, again you should see that this is actually a symmetric top. The reason is the three chlorines actually form the base of an equilateral triangle, and then the carbon is, the hydrogen bond is above. Tetrahedral molecule, if you put the three molecules as the base of an equilateral triangle, then it does not matter whether the axis is this or whether the axis is that. All the three atoms are away from those two axes by the same distance, and so is the hydrogen because it is in a plane. Therefore, two of the moments of inertia are right away equal, and the third moment of inertia, which is the moment of inertia along the CH bond, the symmetry axis of the molecule is different. Okay? So, this is a symmetric top. And S of 6, octahedron. When I talked about cube and symmetry of the tetrahedron as half of the symmetry of the cube, octahedron has the same symmetry as that of the cube, because those are the 6 midpoints of the faces. Therefore, it does not matter whether you draw the axis about any two of these atoms, the moments of inertia for all these three axes will be identical. So, S of 6 will be a spherical top. Okay. CH2Cl2, we notice that it is an asymmetric top because it has only the symmetry of a two-fold axis. Molecules which have only two-fold symmetry, as a rule you can also try and remember, will have to be asymmetric tops. Molecules need a minimum of a three-fold axis in order for them to be a symmetric top. Ozone has only a two-fold axis symmetry, the bond the bisecting the bond of the oxygen, 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 and therefore that you can see right away that ozone is, these two are asymmetric tops. HCN, no problem, it is a linear molecule. Therefore, two of its moment of inertia are the same about the axis, both axes are perpendicular to the HCN bond. It is a linear molecule. Therefore, there is the carbon nitrogen. So, I would say that the center mass is here and the other axis is that, but about this axis the moment of inertia is 0. So, therefore, it is a linear molecule, and last C2H4 also has only two-fold axis symmetry. So, despite the fact that it looks to be very symmetric, this is an asymmetric top, because the axis here and the axis here, the atoms are at different distances compared to those, and the third axis is of course perpendicular to the plane of this molecule. Therefore, it is an asymmetric top. So, the purpose of this video tutorial is to tell you a little bit about how to look at problems from the point of view of not just solving them, but in terms of relevance of these problems in understanding the concepts and so on. And therefore, I suggest that you solve many such problems by yourselves, and if you have questions, please feel free to write that in the forum. I wish you all the best. Thank you.